Hello and welcome back to PC Retro Programmer. In a previous series of videos on the channel, I attempted to get an analog of CGA mode 4, the 320 by 200 4-color mode, that is linearly addressed. By that I just mean all the pixels are one after the other in video RAM with no bank structure as we're used to seeing in CGA. Now, unfortunately, we were unsuccessful in our goal. We managed to get a half screen mode that was linearly addressed. But in order to get a full screen, we'd need the CRT controller to take all of the scan lines from the bottom half of the screen from the odd bank in video memory. And unfortunately on CGA, the bank corresponds to the scan line of the character that the CRT controller thinks it's displaying. Remember, the CRT controller is a character device essentially, even in graphics mode. And unfortunately, there is no register in the CRT controller to tell it which scan line of a character to display. You can tell it the maximum number of scan lines per character, but basically if you wanted to display scan line 1 of a character, you need to start at scan line 0 and let it count up. And so it seems impossible that we can actually achieve our goal on CGA. Now, more recently on the channel, I learned quite a bit about the CRT controller and how it works from Reanigne, and I used this knowledge to get a linearly addressed mode on the Tandy 1000 SX in the advanced Tandy 1000 SX graphics programming series. And I recommend watching that video because I discuss a lot of that knowledge that I gained and the terminology that we're going to use in this video. And we were actually successful in getting a linearly addressed mode there, albeit because the Tandy 1000 has features that CGA doesn't. On the other hand, it is an extension of CGA, and so all of the knowledge that's there is relevant, and I actually explain it there in terms of CGA. Now, I have to say up front that I don't know if we're going to be successful in getting a linearly addressed mode on CGA, but I am now much more hopeful than I was previously. I actually ended up taking a week of leave from work and got so interested in this topic that I spent the whole time studying this. Now, I haven't managed to conclude that work yet, but I've learned an enormous amount along the way, including what some of the ancients knew back in the early 90s, and I have to say it's more than I do. Basically, I now have a bunch of new tricks that I didn't know before, and those are certainly things I want to show on the channel. And that's the real aim of this series, is to learn as much as we can about the CRT controller, and I think this makes an excellent topic, albeit a very advanced one. Now, I should say up front that I don't have any responsibility if anything I show in these videos damages your hardware. I have heard stories of people fiddling around with the CRT controller registers and getting the thing completely out of sync and actually ending up damaging their monitor. I don't think this is a problem for a lot of monitors, but there seem to be some out there for which it is. Now, the other thing that I should say up front, apart from the fact that I don't know whether this is going to be successful, is that even if we are successful, the result is almost certainly not going to be useful. The main advantage of a linearly addressed mode is performance, and clearly we're going to need to intervene every scan line to force the CRTC to display scan line 1 of the characters that it's showing. And this is going to be a lot of babysitting. In fact, it's even going to be quite tight timing at times. And so this means it's going to be both a difficult thing to achieve and also very CPU intensive and therefore not performant at all. But as I said, the advantage here is to learn a heap about how these things work and how we can exploit them to do all sorts of cool tricks. Now, in terms of the structure of today's video, there are three things that I want to do. The first is to discuss what we can hope to achieve in the best case scenario. And depending on the approach that we take, there may actually be some restrictions there. The second thing I want to talk about is how we're going to get to our first implementation, what the strategy should be. And the third thing is to actually write some code that we can actually build on in later videos. Now, first of all, what is the most important requirement for a linearly addressed mode? And in my opinion, it is that all the scan lines should be equally spaced throughout video RAM. Now, this has some consequences. For example, I don't think you could have a scan line that straddles the boundary between the two banks at the 8 kilobyte mark. If half of the scan line is in the first bank and half in the second bank, we'd actually need to change banks from bank 0 to 1 in the middle of a scan line, and that's clearly not going to be possible. One way around that would be to break that scan line into two smaller scan lines, one of which is entirely in the first bank and the other of which is entirely in the second bank, and then just display those two shorter scan lines next to each other on the screen so that they fill out a full raster line on the display. Now, that is an approach that might work, and we'll consider that in a later video. The other possibility, of course, is to consider that boundary at the 8 kilobyte mark between the two banks to be a hard boundary, in that it also has to be a boundary between two consecutive scan lines. Now, one way we could achieve that would be to take the 8,192 bytes of the first bank and divide it evenly by the number of scan lines that we want to get the number of bytes per scan line. Or alternatively, we could start from the number of characters per scan line that we want, which would give us the number of bytes per scan line that we want to display, and divide that into 8,192 to figure out how many scan lines we should use. Now, the problem here is that 8,192 is a power of 2, and that is only divisible by other powers of 2. And this means that the only reasonable value that we could pick for the number of characters per scan line would be 32, which is a power of 2. Now, that's well short of the 40 that we'd normally use for a 320 by 200 mode. In fact, it would only give us 256 pixels across in the horizontal direction that are actually displayed. A little bit later in the series, we're going to realize that even this is probably not quite possible. We're going to have to blank some pixels on the line, so we'd actually end up with even fewer than 256 pixels actually displayed. Nonetheless, despite the restrictions, this is the easiest approach, and it's probably the one that we're going to start with. But the issue now is that when we divide 8,192 by 32 characters per scan line, or 64 bytes per scan line, we end up with 128 scan lines in the first half of the screen and another 128 in the second half. Now, that might be a few too many. They're not going to fit on the display, and so we're going to need to cut something short somewhere. One thing you might have thought of is to start a little bit late in the first bank. Instead of starting at address 0, we could set the start address registers to a slightly later address and start our scan lines there. And that would actually give us a value less than 8,192 that we'd have to divide evenly by the number of characters per scan line. And this might actually give us other possibilities than 32. So it could allow us to rescue a few more pixels across the screen. So that could be a convenient approach. Of course, we have to think about what happens when it gets to the end of the first bank. It'll wrap around and it'll start getting data from address 0. And at that point, we'd have to convince it to use the second bank instead of the first. And so it would actually be getting data from address 0 of the second bank. Now, that sounds ideal because that's exactly what we want it to do. We want the next scan line to start at exactly that point. So possibly this is an approach that we can follow. Of course, the other way of handling things would just be to start with 128 scan lines of 256 pixels across to fill up entirely the first bank, and then just not use all of the scan lines in the second bank. We just set the number of displayed scan lines to something less than 128 and just not use up the whole of the second bank. So that's also a possibility that might work, and for reasons that we'll see a little bit later, this is actually the one that we're going to start with first because it's also the easiest. Now, the next thing we need to discuss is our strategy for solving the main problem that faces us. How are we going to get the CRTC to assert row address 1 for essentially the entire bottom half of the screen. And when I tell you the answer to this, you're probably going to laugh because it's not that hard. The CRTC will assert row address 1 immediately following any scan line of row address 0. And so what we're going to do is we're going to put some dummy scan lines, very short ones, in the border region that aren't going to display any pixels that are row address 0. And so immediately following that will be our main scan line where all the pixels are displayed, and that will be row address 1. And you might ask, well, is that even possible? Well, yes, it is. Of course, it requires a lot of babysitting. We have to rapidly switch between these short scan lines in the border region and these big scan lines where all our pixels are. But we can do that, and it's made easier by the fact that we're only going to have 256 pixels across in the horizontal direction. So our border regions are actually going to be quite large, and there'll be plenty of time for us to set everything up. And that's why I've chosen this approach first, because it's much more feasible than doing things with much tighter timings and narrower borders. Now, I don't want to go into the details, but for those of you who've heard of a technique called RVI, this would be a possibility here, except that on the PC it's extremely difficult to pull off, if not impossible. And that's due to the cycle precise timing that's required, which is actually very hard to achieve on the PC for reasons that are best left for a video if any of us ever get it working on this platform. Well, now that we have a strategy all worked out, which seems like it should be straightforward enough, let's take a look at the first lot of code I've written for this, linear7.ism. And unfortunately, we're quickly going to discover that this task is harder than it seems at first. In fact, at the end of this video, I'm going to leave you with a little bit of a puzzle to ponder before the next video. We're going to encounter some rather strange behavior, which at first sight seems quite difficult to explain. And it actually took me a number of goes before I figured it out. Now, the code that we're starting with here is a modification of the code that we had in the previous video on linear addressing on CGA. We're still setting things up with one scan line per character and with 200 displayed scan lines using the trick that I explained to make it count past 127. But there's one major change that we're going to make. Instead of using timer interrupts, we're actually going to count scan lines. Now, the reason we don't want to use timer interrupts is that they're just too expensive. It takes too long to handle the interrupt. There's not enough time left to do everything else that we need to do. When we're in the bottom half of the screen, we're going to need to intervene every scan line. In fact, twice every scan line, because we'll have two smaller scan lines for every raster line on the screen. And this is just too much to have a timer interrupt for each of those. Even if it was possible, there just wouldn't be enough time left to do all of the register updates that we're going to need to make this effect work, if in fact we can do so. Now, the code is pretty straightforward at the beginning, but there are some issues that arise from counting scan lines, and we'll see those a little bit further down. But first of all, how do we actually count scan lines? And the answer is to use the CGA status register at port 03DAH. One of the bits there gets toggled every time we go from an active region where pixels are being displayed to a blanked region where nothing is being displayed and no data is coming from video RAM. And of course, every scan line has an active region where the displayed characters are and then a blanked region. And so we can count scan lines just by counting the number of times this bit toggles in that status register. As I said, this is going to cause a few problems for us. For example, we're going to have to turn interrupts off because we don't want our very delicate counting operation to be interrupted, as it were. And with interrupts off, this means that we can't access the keyboard, so there's no way to quit the program. So I'm going to show you a way to work around that as well in this video. At least the start of the code is fairly straightforward as it was before. We set up the CGA segment address, we change into CGA mode 4, and we put 0 for the offset into the video RAM. And then we're going to fill up both banks with some data just so that we have something to look at. But I'm going to put different values into the first bank and the second bank. And the reason for that is I want to be able to tell when I'm getting data from the second bank displayed on the screen. At first, we're just going to have row address 0 everywhere, and so we'll only be getting stuff from the first bank. So in fact, at first, we're only going to have cyan and black displaying on the screen. It's only when we're actually successful inserting row address 1 on the bottom half of the screen that we're actually going to start to see magenta and black on the bottom half, if we manage to get this to work. Now, the reason that I'm alternating between cyan and black is because I want the background color to actually show through. And the reason for that is I'm going to use the background color as a kind of diagnostic tool. It turns out that when you set the background color in CGA, this takes effect almost immediately. And so if you want to know where you are up to within a frame, and you want to be able to see that visually, just change the background color in your code, and then you know exactly where that piece of code corresponds to on the screen in time, so long as that change of background color happens at the same place every frame. And so this is why I need color 0 here for some of the pixels, because I need that background color to show through so that I can see when I actually change it. Now, the next thing that I want to do is to turn interrupts off, and that's because they're expensive to handle, as I explained. For example, if you load the program off floppy disk, shortly after the program starts, the floppy drive will need attention to turn the light off. And so this is already an interrupt that we have to worry about. The keyboard could be used, the mouse could be moved, there could be other interrupts occurring like the hard drive, and there's also the DOS timer interrupt. And so we really want to turn all of these off. Now, of course, this means that we won't know when a key has been pressed on the keyboard because that's done via an interrupt. And so we'll need to use some special tricks in order to manage that. But I'll show you how that works a little bit later. Now, the next thing we want to do is to set up some CRT register values. We'll set up the vertical total, vertical displayed, the number of scan lines per character, and so on. And eventually we'll also change the horizontal displayed to 32, corresponding to 256 pixels across in the horizontal direction, as I explained earlier. Now, we're not going to do that initially. We'll just stick with the default value of 40 that we get normally in CGA mode 4. And so this code is actually commented out for the time being, but we'll come back and see what the effect of turning this on is a little bit later. Now, you can see I'm putting O3D4H into DX here. That's a 2-byte move into a register. But from here on in, I'm just going to assume that 3 is in DH, so that if I need to change the port address to one of the other CGA registers, then I'm just going to change DL. I'll assume that the 3 is already there. And this will save a byte of machine code each time we do this. And we really need to skimp and save wherever we possibly can here because of the ultimately very tight timings we're going to have. Now, the first thing that I'm going to do after this is to wait for vertical retrace so that we know where we are on the screen. And this is done by looking at port O3DAH at bit 3. And basically that'll go non-zero when we're in vertical retrace. So we just test that bit 3 by testing it against the value 8, which just has a 1 in bit 3. And whenever that's 0, we just loop around. And finally, it'll go non-zero when we're in vertical retrace and fall through. The next thing we need to wait for is the first active region. So this will be the start of the first scan line that's displayed. And here it's counterintuitively the other way around. Basically that will go to 0 when we're in the active region. And so when we're non-zero, we'll loop around. And this is bit 0 of port 3DAH that we need to be looking at. So the next thing that we will do is to change the register values I was talking about. So this is port 3D4H again. And the first thing is to change the number of scan lines per character to 1, which means putting 0 in the maximum character scanline value. And then we need to change the vertical adjust to 6. We'll have two regions of 128 scanlines. We'll do that by setting the vertical total to 127, and you remember that 1 always gets added to that value. So 2 times 128 will be 256. It's not quite the 262 that we need for CGA, so we have to put 6 in the vertical adjust register. And as I said, 127 in the vertical total actually corresponds to 128, but we are going to allow it to wrap around so that it'll actually count twice, and that'll give us a total of 256 that we need in total. And initially, we're going to set vertically displayed to 127. Now, this is not because we actually want 127 scanlines displayed. We're going to change this so that it wraps around, and then we'll change it to a value of 72, and with the wraparound, which would happen after 128 scanlines, that would give us a total of 200. And we'll see that extra 72 displayed scanlines a little bit further down. So all of this has now happened on the first scan line, and from here we're going to have a big loop where we start counting scan lines. Now normally we'd start from the first scan line after the vertical retrace, and you'll see in a moment we check for vertical retrace and start counting scan lines. But at this point up here we already know we're on the first scan line, and we've already changed some registers and so on. So there's no need to check for vertical retrace again and wait for the first scan line because, well, we're already on it. So we're actually just going to skip over that the first time around, right down to where we start waiting for the second scan line. And so you'll see there's a little label down here which has us waiting for the second scan line. So now let's take a look at how the CRT loop works. It's essentially what we just did. We wait for vertical retrace, we wait for the first active region, and then we're ready to change registers. Now additionally on that first scan line, we want to also change the vertical sync position to 127. And again, that's not because we want a sync at 127, it's because we just want to put it out of the way so it's not actually reached. We'll move this to another value later on so that the wraparound can happen without a sync pulse, and then we'll set it to a value that corresponds to the position where we really want the sync pulse to be. And this is exactly what we did in the first video where we did 200 scan lines. Now, after the end of the active region of the first scan line, we also need to check for the non-active region. So we wait for that to happen, and once we're in the non-active region, then we can start looking for the active region of the second scan line. So from here, we need a little bit of a gap. We don't need to do anything for another 96 scan lines. And so I have a loop here that counts down from 96 to 0. And all it's going to do is just wait for active, wait for non-active, wait for active, wait for non-active. And I'm using the convention that my labels here have the starting scan line and the ending scan line for this loop, inclusive. So basically this loop is taking care of scan lines 1 through 96, and it just checks for each of those by waiting for an active region, then a non-active region. So that's all that is about. And so now we're going to wait for the active region of scan line 97. Now on scan line 97 we need to do some things. We need to move the vertical total to a lower value so that it's not reached the first time around. This is to trigger an overflow so that it wraps around and starts counting back up again. And we need to put 72 in vertical displayed After all, 128 scan lines from the wraparound plus that 72 will give us the 200 displayed scan lines that we want. And we're also going to now change the vertical sync position to 95. Now notice 95 is also below the current scan line. We're at 97 at the moment. And so it's not going to be reached the first time around either. The position where we really want it to be the second time around is at 95. And so we change that now here. And then we wait for the non-active region of scan line 97. And then we have 102 more scan lines that are actually going to be displayed. And so these are scan lines 98 to 199. So we just use our trick of having a loop again that just waits for active, waits for non-active, waits for active, waits for non-active, and so on until we've done 102 further scan lines. So that's all of the displayed scan lines on the screen, and now we're just in the vertical blanking period. And so once we're into the vertical blanking period, then we need to change the vertical total and vertical displayed back to 127 again, which is what's expected at the start of our big CRT loop. So hopefully that's fairly straightforward, and from here we just loop back around to that CRT loop label at the top of this big long loop. And so it's just going to keep going through all of the scan lines on the screen over and over again, changing these values on exactly the right scan lines so that it does its overflow and wraparound and so on. But of course, then we have no way to end the program. Remember, interrupts are off, and so we can't press a key on the keyboard to stop. So the way this is done is to actually deal with the programmable interrupt controller, the PIC, directly. And it turns out that it actually has a register in it which shows if any of the interrupts has been requested. It's not passing those on to the CPU at the moment because we have interrupts off, but we can still look at that register and see whether any interrupt requests were made on any particular lines. Now, the keyboard interrupt comes in on interrupt request line 1, which would correspond to the value 2 when we use a test here. So the register itself is called the interrupt request register, and we access it via port 20H. So I'm not actually going to go through all of the different values that you can pass out to port 20H. It's just a magic formula for now. If you pass the value 0AH out to port 20H, this tells it that the next command read will be for the interrupt request register. There's a number of registers that it can actually access here. And so then we do a read from port 20H, and that gets the value of the interrupt request register. And each of the bits here corresponds to one of those interrupt lines. And as I said, interrupt line 1 is for the keyboard. So we test if that bit is set, and if it's set, the value is non-zero, then that means that there was a keyboard interrupt, which presumably means a key was pressed. And so then we can jump out of our big CRT loop and end our program. So in fact, we'll jump over the bottom of the loop here down to this label and turn interrupts back on again. It'll actually handle that key press that we made, and then we restore the text mode and exit to DOS. So that's all we're going to do in the first iteration of this code. So let's actually save this and assemble it and see what happens. As usual, we'll assemble the file and link it, and then we can actually run it here in this emulator. This is a 286 emulator, but it has CGA, and we'll just make sure it all works here before running it on real hardware. And everything looks fine here, and when we press a key, it exits to DOS. Just off the top of my head, I don't know why we end up with the C prompt twice here, but it's something to do with the way that we're dealing with that interrupt that comes in for the keyboard. Anyway, let's run this on genuine hardware. By that I mean IBM PC with a genuine IBM CGA card, or at least something that's 100% compatible, and we'll see what happens. Well, here we go. Let's see what actually happens. And there's no surprises there. It looks like we have a full screen with blue lines down. Every scan line's the same, and of course everything is still from bank 0 at this point. The floppy light, by the way, is remaining on, and that's because it hasn't been able to deal with its request to turn the motor off. So I'm going to press a key now and just check whether we're getting the keyboard working, and indeed it does. And as you can see there, we also get the A prompt twice again. As I said, I don't exactly know why that is. It's another puzzle to think about for next time. And now let's make the change that I talked about before, where we change the number of horizontally displayed characters from 40 down to 32. So it's just a matter of uncommenting these two lines here, and we'll assemble and link the code again. So t-link linear 7, and let's just run it in the emulator again just to see that it's actually working, and everything seems fine, although notice that for some strange reason the emulator isn't showing a black region on the right hand side as you would imagine if it was only displaying 32 out of 40 characters now. So that's a little bit odd. But now let's run this same code on genuine hardware and see what happens. Well, here goes. Let's see if it's any different this time, and look at that. Something weird is going on here. So we do see that it's now 32 characters across in the horizontal direction, but we've totally lost sync. And I actually don't recommend running this code, by the way, but I know that my monitor is fine with this. I've had it out of sync for quite some time and it really hasn't made any difference. But the real conundrum here is, why is it out of sync? If I change to 32 characters per scan line in ordinary mode 4, then I would have no problems at all. It would display just fine. So how on earth can 32 characters in the horizontal direction instead of 40 possibly mess up our timing? So that's the puzzle that I'm going to leave you with until next time, and I'll explain exactly what's going on here, which, by the way, isn't obvious, although you certainly do have enough information at this point to figure out what the problem is.